Okay, before I proceed, can someone from Zoom confirm if I'm audible? Okay, good. Okay, so thank you everyone for joining the presentation. So I will start with my trial lecture topic, which was assigned as the role of neural network in model predictive control of power converters. So this will be as a part of my PhD defense. So the outline that I will cover for this presentation, I will give you a brief background of the work. Then we will see how the model predictive controller works for power converters, what are the limitations, and how we can address them using the neural network. And at the end, I will be providing some summary of the work. So let's start with the introduction first. And maybe the simplest possible example that one could come up here is the converter connected to a grid through RL branch. So the intention, the objective here is to inject a sinusoidal. So the objective or intention here is to inject a sinusoidal current to the grid, but by following the reference current. So here is a star because it's a reference value. So we will inject this sinusoidal current, but how we are going to do that? We will measure this inductor current or the output current and compare it to the reference value and process it through a linear controller. So in principle, what we are doing here is we are manipulating this current error to convert into a reference voltage signal, or you can say the modulating signal. So, and the reference voltage signal is ideally expected as a sinusoidal again. So, but if you'll notice here, the power electronics converter switches are in discrete in nature, right? So for that, we need to convert this reference voltage into switching signal through a modulator. So now, while doing that, we may expect some ripple in the output current waveform. However, we can solve that by using the carrier-based PWM technique. There are some other PWM techniques as well, but I will not go into the detail of that. But what it is happening here is, whenever the reference signal intersects the carrier signals, then we will be doing the switching. So that is for positive half, and samely we can do for the negative half. So with that logic, if we are going to do the sampling at the point of intersection point, then you can notice here we are somehow neglecting the current ripples, and we will end up getting the fundamental component only. So that means we are actually hiding the switching logics that are introduced by the modulator from this linear controller, and that is very interesting because the linear controller doesn't have to know what are the disturbances happening during switching. So it will only assume it is taking the sinusoidal input and it is converting a sinusoidal reference voltage. So that's how the controller and modulator works for a converter. But if we'll talk about the model predictive controller, then it gives a very different vibe, different concept of control theory, because it can actually merge the controller and the modulator into a single control platform, and it will just receive the feedback of the current signals, and it will directly give you the switching instances or switching pulses to control the converter. So the advantage is not limited to this only, because ideally what you expect, you are connecting renewable energy sources at the input of the converter through a DC link. So the maintaining the DC voltage balance is another issue, right? So for that, you are actually defining multiple linear controller loops to maintain the DC link voltage balance, and you are making them interact different linear controller loops to produce the ultimate switching logics. However, we can do all those stuff within a single control algorithm that is called model predictive controller. So we will see how it works. But before that, I will just give a brief background how the MPC in general works. So if you have searched or came across the model predictive controller, then this is a popular diagram that will pop up. So initially, when I got into MPC, I found a little difficult in understanding this diagram, but I will make it simple here. So for any control problem that you are controlling a system, you have a set point or a reference value, you can say. So our target is to reach at the set point or the reference value. And for that, you receive some sort of control inputs. So what MPC will do, it will receive the control input at this particular instance. Let's say it is kth time instance, kth sampling period. So it will receive that particular input signal, and it will do the prediction up to certain control horizons. For example, I have defined the control horizon as n. So it will take the input signal at this instance, but it will predict what could be my possible control inputs up to this much of horizon. So that accordingly it will say, yeah, we can actually reach at the set point precisely and also very fast. But you only have the option that you can only take one sample at a time. That means, although you have predicted your control input to be up to here, you will only take the fast input signals, right? So then two question arises here. You are predicting up to here, but you are only taking the fast input signal. Then what's the point of predicting this much? And the another question is, why not the last one? Why you are only taking the fast control signal? Because if you are waiting up to here, if you are planning to take this signal as an input, you need to wait this much of time. And that we don't want. That's why we are taking the fast predicted signal. And what's the point in predicting this much of up to n number of control horizon? That's because we want to do some prediction in our mind so that we can actually precisely reach at the reference value. I will relate it to a real chess game. Let's suppose your opponent made a move. Then based on that move, you are planning or predicting certain set of moves, right, in your mind. But you will only apply the only one move. You are allowed to apply only one move. So that's exactly what MPC is doing here also. So with that, I will go to the MPC application for the power converter. It actually exactly works the same way for controlling the power converter. But the first step of MPC, working principle of MPC for power converter is defining the switching vectors and switching logics for that. So let's take an example, the two-level three-phase voltage source converter connected to a grid or load. So that means we are going to have 8 switching states, and that will correspond to 8 switching vectors. However, I have written 7 switching vectors because the first and the last switching vectors are going to end up at the same position. So you can actually say 7 switching vectors. And we will define the switching states. Let's suppose this leg belongs to the state SA, and similarly this leg SP, and similarly this leg SC. And in each of the leg, you can actually turn on the switch only one at a time. The other has to remain off. So with that logic, you can define these conditions. And then how the switching vectors are related to these switching logics. So if we'll see it here, let's consider this vector V2, which is 110. That means SA is 1, SB is 1, and SC is 0, which means this S1 switch, S2 switch, and S6, these three are conducting to produce your output converter voltage. So that's how these two are related. So this is the first step of defining a model, defining for model predictive control. Then the second step is to define a discrete model based on which you can actually predict your input signal. So how we are going to do that is very simple. We will just apply the if you are running into a grid following mode, you will just apply the KVL equation here, which takes into account, which says that the converter output voltage is the summation of the voltage drop across the RL branch plus the PCC voltage. And if we'll do a little arrangement, then we'll end up with this differential equation. However, according to the forward Euler approximation, we can actually discretize any differential equations. So this is the way how we can do, where TS means the sampling period, and it is the system sampling period, not the control. And now if we'll compare this equation with the discretized uh, equation, then we'll end up getting the predicted input current, which is mentioned here. This means we got the expression for we are actually receiving the control input at the kth instance, but we are predicting the current at the k plus 1 instance, right? So from the second step of the MPC, we will predict the control input and we'll use it to solve the cost function, which comes as the third part of the model predictive control. So if you'll notice it here, the cost function that we have defined here is uh, difference between the reference current and the predictive current, because that's our objective. We are going to manipulate our output current that it is following its reference value. So this will we have written P here because this means it's the predictive current. So to summarize all the three steps, what is happening here? We are measuring the current, which kind of acts as an input at the kth sampling time, and we are using the predictive model of the system to predict the next sampling instance of your control input. And you will use those predictive signal for all the 8 switching states that we have defined at the first step of the MPC. So, and those 2 steps, we are going to merge it in the cost function that is defined here, and we will solve the cost function, and the switching instance that relates to the minimum of the cost function that will be selected as a final control output. So whatever I said or summarized here, we can actually understood it in a better way if we'll consider an example. So these are all the 7 switching vectors, and data and corresponding cost functions are also listed here. So let's suppose we have applied the voltage vector V0 to predict our inductor output current and to calculate the cost function G0. So that has resulted the cost function value to be 0.6. I actually took this example from the reference mentioned here. So yeah, then similarly, if we'll use the vector V1 to predict the current I1, and that will result the cost function G1 to be 0.82. Similarly, we'll do all the calculation for the all 7 switching vectors. So on and so forth, we will end up calculating up to G6. Then from here, you can notice the minimum cost function value that we got is related to V2 vector, 0.24. That means for the next sampling period, we are going to assign the switching pulse signals that is related to this V2 switching vector. And if you remember it, this V2 actually relates to the S2, S4, and S6 of the switches of the converter. So that's how the model predictive control works. But we will see how the real advantage comes into the MPC, brings the MPC to the table. Let's suppose consider a multi-level converter. Here I have, just for an example, I have considered neutral point clamped converter, where you are going to have 2 DC links, and you are willing to maintain the same voltage across both the DC links. If it is a linear controller, you just add 2 linear loops and make them interact. However, if it is MPC, you just have to define an additional cost function or additional objective in the earlier defined cost function. That's it. No more science behind it. Since a NPC converter, you are going to have 27 switching states, and you will solve the cost function for all the 27 switching states. So for an example, we will see, okay, we actually assigned a weight factor for, since we are now controlling 2 objectives. One is to control the DC link voltages, and the other is to maintain the inductor current so that it follows its reference value. That means we need to weight and as a weight factor so that we can give importance whether we are giving weightage to maintaining the DC link voltage balance, or we are willing to give more importance to the inductor current that it follows the reference value. So for that reason, we have assigned a weight factor here. So now the tricky point is we need to tune the weight factor accordingly so that it will produce the better results. So for example, if we'll see here, if you make this lambda DC to be 0, then you end up losing the balancing torque. That is why both the voltages are not same anymore. However, if you'll assign a certain value to here, then you are getting your both the DC links to be settled at the same value. So this is an advantage of the MPC and also can be a disadvantage of the MPC, because if you are going to solve a larger, if you are thinking a larger aspect of the system, you are going to have several objectives in a system, right? So for that, you are going to assign several weight factors, and tuning them is very difficult. So that is one of the limitation of the MPC. The other one is it is very computationally heavy because it is kind of an optimization algorithm. It solves certain set of system model at every sampling instance. So these are the two limitations that possibly we can handle it in different way. But one of the suitable choice is to go for the neural network, because if we'll see here, uh, let's consider we are actually solving an objective function that has three weighting factors. And the weighting factor values are ranging from 0 to 10 with a step size of 1. So that will result 1,331 kind of possible combination of weight factors. So you cannot actually do it in a trial and error basis. And we are also not going to use another optimization algorithm to predict this switching weighting factors for you, because MPC itself already an optimization process, and you are adding on top of that another optimization. So the controller will go mad. So to avoid that, we have you can actually use a neural network, because it is just combination of certain mathematical equations. Very, I mean, just multiplying the weight values and addition based bias values. We'll see that. So that is one way of using the neural network for MPC to address their limitation. So before jumping into the problem, I will just give you a brief introduction about the neural network, how it works, what kind of type exists. So the first question is, what is a neural network? If we'll ask a data science researcher, they will say it's the same thing as of the human brain. But for us, the power tennis control guy is just a function approximator. Whatever you are feeding the logic to it, polynomial function, it will just try to fit it. That's it. And the keywords that you need to memorize for a short time is number of neurons, number of layers, and activation functions, because those are the things that I am going to use more in the upcoming slides. So these are some sort of typical example of activation functions. And also, what are the major types that are getting used for the power electronics control are mainly supervised learning and the reinforcement learning. So in the supervised learning, we are kind of using a level data to generalize the on-scene data. And in the reinforcement learning, you are kind of acting as an learning agent that will be assigned within a reward function. So if we'll predict in a good way, your reward will be better. But for the timing, we have only focused on the supervised learning type, because that is a thing that is used many times in the literature for power electronics converter application, and it's worth for supervised learning. Stick to supervised learning until and unless your problem is too complicated that cannot be addressed through it. So this is a typical example of feed forward supervised learning type. What it is doing here is it is consisting of three layers: input layers, hidden layers, and the output layers. So you are going to store your input variables in the input layer, and the hidden layer could be combination of several layers, could be one or could be two, three, and also can contain multiple neurons in the hidden layer. And finally, it will predict the variables that will be stored in the output layer. So what is the science going within the hidden layer is you will multiply or you will assign certain weight values to your inputs. So that means the inputs will get multiplied with the weight values, and afterward it will get added with certain set of bias values, and those weight and bias values will get it through the training process. So we will process the final outcome through an activation function. So in the power electronics control domain, the linear activation function and the hyperbolic tangent, those are the two major types that are used for the supervised learning feed forward type. So we are going to use it here and then repeat the same procedure at the output layer, and then ultimately you will get the predicted output. So let's take a toy example to understand, because the data plays a major role in the working of the neural network, right? So let's suppose this is just for the presentations, not the exact trained model of the ANN. So if it is a supervised learning and you are providing a one feature, which is square meter. So per square meter, what will be the cost of your house in Norway or in Nordic countries? So you have provided this much of data to your supervised learning and you are asking it to predict it. So what it will do, it will just do the calculation of slope, because you only fed it to only one feature, that to which is square meters and with less number of data. So it will just draw a line. As I said, it's a universal function approximator. However, if you are going to feed it more input parameters, let's suppose say you are also on top of giving the slope value, you are also giving the y-intercept. That means how far it is from your slope. So it will get a bit better prediction from here to here. But still, if we'll provide more data, better training. If we'll consider it as an polynomial, higher order polynomial, and provide more features, more data, then you are end up getting better prediction. But that doesn't mean will give a huge amount of data, consider huge number of layers. It will end up like this. And this is kind of overfitting problem. So that is a big challenge in the neural network. With that, let's take an example how the neural network is addressing the issues or limitation of the model predictive controller. As I said, tuning the weight factor is a limitation or drawback of the MPC that we are going to address through the neural network. So for that, let's again consider a neutral point clamp converter, where you are having so many. This is kind of fancy model predictive controller that is reported in this paper. So with this kind of cost function, they are achieving basically better performance compared to the standard MPC. So if we look into the terms, they are considering since it's a standalone system, it is not connected to the grid. So they are controlling the voltage instead of the current. So they are considering the voltage in the PC's voltage and corresponding reference value in the cost function, and its derivative term that actually gives a better performance. And this one is related to the DC-link voltage balance in both the DC links. And the last one is switching frequency. You want to, because MPC has a variable switching frequency logic, so you want to limit it up to a certain range. So basically now we are going to feed the input data, output data to the neural network, which will predict what are our weighting factor lambda D, lambda DC, and lambda SW is going to be, so that we can achieve a better performance. But there comes the tricky part again. What are the input parameters we are going to choose to train your neural network? So based on my observation, why they have used THD, VDC error, and FSW is, if we look back into the cost function, it contains the voltage difference of the PCC voltage and reference voltage and its derivative term, the first two term. So you need to choose some parameter that can actually relate to this PCC voltage. So since there are two terms, so what they have done is they calculated the THD of the PCC voltage here, and they are giving it as an input parameter for the ANN. And the second is second weighting factor is related to your maintaining the balance of the DC-link voltage. So that is why you see the VDC error is going as another input to the NN. And the last one is average switching frequency. So with several data that you are going to collect by simulating the model predictive controller, you will predict these three weighting values. So as I said, they have implemented the MPC and executed it for 0.5 seconds. And for this many number of combinations, they have noted down these input parameters to train the NN. So as you can see here, the regression value, it indicates, I mean, it's very closer to unity. That indicates your ANN is successfully trained. So it can be deployed online. That will predict your or tell you what is the accurate weighting factor combination that you are supposed to use so that you will achieve better performance. So for the representation, I took this result from the reference. So what it is doing here is the fast result is obtained with the fixed weights. Your weights are fixed with a certain trial and error based method. But the second result, they are obtained with the ANN tuned weight values. So if you'll notice here, the voltage error of the PC's voltage with respect to reference voltage, they are actually minimized compared to the untuned MPC. So, and also it has been observed that the THD and also DC-link voltage error and also its performance during dynamic or transient conditions, those stuff are also improved when we use the tuned weights through the neural network. So this was one of the case study that neural network can address the problem of the MPC by tuning its weight factor. Then what could be other studies? What researchers thought, let's not tune only the weight factors of the MPC. Why not replace the whole MPC? Because it's already kind of an optimization algorithm. We just replace it, achieve the same performance as that of MPC, and also at the same time we are reducing the computational burden. So that is what it is I'm going to discuss here. So with same set of parameters, if we'll process through a neural network, that will follow the linear path instead of solving some optimization stuff, but it will predict almost the similar outputs as that of MPC. So that is interesting because it has been observed that for a single phase 5-level multi-level converter, the number of calculations ANN made is actually almost 200 times percentage times reduced compared to the MPC. And also it requires 15% reduction in computation time in the PGA source. So those are the two conclusions that are reported in this paper. So that is why they use the ANN to replace MPC. So let's take an example how it is being done. So again, we will implement the MPC algorithm to control the converter here. So what are the input data that we are going to feed is the output current, voltage error, the PCC voltage reference and PCC exact actual PCC voltage, system model, and the present switching sequence. So those are the eight inputs that we are going to feed as an input to the neural network. And what it will predict is the switching sequence at the output. So we will execute it for certain duration of the simulation, collect all the input and output data, and train the neural network. So once it is trained, you deploy it online to control the voltage source converter by removing the whole MPC controller. So if we'll see it here, one of the results that I presented here is under the load changing condition. So if we'll see the results that are obtained with the MPC controller, they are exactly mimicked or predicted by the ANN controller here, right? At the same time, it is actually reducing the execution time. So if you'll notice here, the ANN controller takes almost twice the less time of the MPC controller. And also the THD value obtained by both the controller are not very far from each other. So that is why not ANN instead of MPC. So those are the two case studies that I have observed in the literature that the ANN can play a significant role in enhancing the performance of MPC or replacing the MPC. So to summarize the presentation, MPC offers a good solution, and also it has the capability of handling multiple objectives in your system. But it comes with certain drawbacks like training the weight factors, choosing the right weighting factor combination, and computational burden. So those are the two stuff that you can actually address using the artificial neural network. But it's nothing comes for free. If NN is addressing something, it is also bringing some kind of drawbacks to you. So it also has its own challenges. What are the challenges? Complexity in training. As I showed the toy example, if you're not feeding sufficient amount of data, then your prediction is going to be very worse. And if you are feeding large number of data, large number of features, then it could end up in getting the overfitting problem. So that will do the wrong generalization. That means under unforeseen conditions, it may predict you the wrong values. So that was it. These are the references that I have considered for this trial lecture. Thank you.
Thank you for a nice presentation. Me and the two other components will have a internal meeting to discuss your performance, and we will come back within 15 minutes. So we'll just have a break.
Thank you.
What's happening now? Is it break or what is it? Is it break now or what?
I think so.
It's gonna be Friday.
You can ask questions.
We can actually discuss.
What is the window they use in this last paper? For the online, yeah. What window? Compared to the fixed one. The fixed